In today's video, we're going to look at section 1.4, which is called the method of least squares. What this topic talks about is finding a trend to data. So there are many occasions where researchers are trying to find data to see how one quantity compares to another quantity. So for example, how savings are affected over time, or how blood pressure increases or decreases as you get older, or how effective a drug is over time. So what they do is they plot data points on an XY plane where the Y quantity will depend on the X quantity. So for example, if we're looking at how our savings are affected over time, we would see that time would be on the x-axis and the savings which are affected over time, savings would be on the y-axis. And then for any particular person, each person would be a data point. So you could see how one person's savings are affected over time, how another person's savings are affected over time, etc. And you can look at years, or you can look at just one person and look between 0 years and 10 years. You could plot data points to see how their savings go up or down over so many years. So it's completely dependent on what you're trying to look at, but the whole point of this is trying to see how something is affected compared to another quantity. So how one quantity compares to another. We'd like to see a trend in this data that we're looking at. That would be ideal. And it would be great if that data was actually linear. The problem is, due to errors and irregularity with real life phenomena, these data points actually rarely fall on an exact line. Okay, in just real life situations, nothing's ever going to really be exact. So you rarely find data points lie exactly on a line. But if we want to assess the data, we kind of want to see what that trend is and see if we can find some kind of linear pattern that it takes so that we can make assessments about the future, what might happen later on, and basically predict other data points, because we can't do that if we've got data scattered everywhere. So if we can figure out some kind of linear trend to our data, it would help us make predictions for future data points. That line, that linear trend that we are looking for, is called the line of best fit. It is the line that best fits the data points and goes through the middle of all of our data points. It may not go through every single data point, but it's going to go through between every single one in the middle. We'll look at an example of this in a second, but the question that we are fundamentally looking at is, how do we find this straight line that best fits our data points? Here is a quick sketch of some data points with a line going through the center of them. Okay? This line may not be our line of best fit, but I kind of want to show you what we are looking for in a line of best fit. You see here we have 3 data points. The purpose of the line that I want to draw is to give me the best approximation for any future data points I want to look at. So, for example, if I want to approximate for a particular time what my savings would be, or for a particular X value what my Y value would be, the purpose of my line is that I can say, okay, at the point X4, so let's say X4 landed here, at X4, this would be a good approximation for my Y value, this Y value here, okay? So the purpose of this line is to give me a good approximation for future data points. So for a particular X value, it will give me a good approximation for my Y value. Okay, that is the purpose of this. Here you see that we have 3 data points. So we've got 3 X values with their corresponding Y values. None of them lie on this line. Okay. What we see from a line of best fit is that we have this line that goes through the center of all of our data points, And we will have a particular vertical distance from our data point to the line. Okay, these are denoted by E1, E2, and E3 in this case. These are the errors. They are the errors of each data point to the line. So how far away the line is from our given data point. Okay. Obviously, for a line of best fit, the purpose of the line of best fit, we want to try and make sure that these errors are as small as possible. So they're as close to as many points as we can possibly get. Okay, that's kind of the purpose of a line of best fit, because that will give us the best approximation for a future data point if we were to predict it. Okay. So we could see that in this random line, again, this may not be the line of best fit. We've just drawn a random line through 3 data points. Okay. We have an error, we'll call it E sub I, for each data point, and that is the vertical distance of each data point from the line. Now, the problem that you'll see with each of these E sub I, so E sub 1, E sub 2, and E sub 3, problem with each of these is that some are going to be positive and some are going to be negative. So when statisticians actually look for lines of best fit, their problem with trying to minimize them is that they can't just add them all together and say, hey, I want to minimize this number. That doesn't work, because some of them are positive, some of them are negative. So that's actually going to cancel them out. Okay. What they actually do when statisticians do this is they actually square each of these E sub I's, each of these errors. Okay. So each of the distances between the lines and the data points. Why do they do that? A squared number is always going to be positive. So if I square each of these distances, regardless of whether they're positive or negative, because a data point can fall above or below the line, if you square them, it's going to be positive. We can then try and minimize the sum of the squares. That way we're just adding together a bunch of positive numbers, and we can try and minimize that number. Okay, because we're not going to get values cancelling one another out. So the sum of squared errors is denoted by a value E, which is just the sum of the squared values of these E sub I's. Okay, this is for if you had n data points. So in our last example, we had 3 data points. Okay. And the point is, we try to minimize this value E to find the line that best fits the data. What happens if this value E is 0? Well, you've got a bunch of positive numbers all added together. If they all equaled 0, the only way that that happens is if every single one of our errors, each one of our E sub I's, was 0. That would mean that every single one of our errors is 0, so all of our data points must lie on a line. As I said, very rare that that actually happens, but if that were the case, then your error would be 0. You would already have a linear trend for your data because all of your data points lie on a line, and therefore you could very easily go ahead and predict future data points. Okay. So if E equals 0, then all of our data points are on a line. This leads us to then finding our what we call least squares line, regression line, line of best fit. Whenever you see one of these terms, it all means the same thing. So it can either be called a least squares line, it can be called a regression line, or it can be called a line of best fit. Like we have said, all of these mean the same thing. It is the line that will go through the middle of our n data points. Okay, it may not go through every single data point, may not go through any of our data points, but it goes through the center between all of our data points. And it is the line such that this error term E is minimized. So it is the line that best fits our data. It is the line of best fit. It is the regression line. It is the least squares line. We can then use that line to go ahead and predict other data points. Like I said here, we could predict what our Y value would be for a given X value. You can find the equation for this line of best fit by hand. It is incredibly tedious to do. You can go ahead, if you look in the textbook, it's on page 27. I think it's at the bottom of the page. Because you're trying to find the equation of a line, easiest way to find an equation of a line is to go ahead and find the slope-intercept form of the line. There is actually a formula to find each of M and B given your data points. So if you've got a bunch of N data points, okay, there is a way that you can find M and B by hand. So you can find the slope and the Y value for the Y-intercept by hand. It is so tedious. If you look at the formulas, they are very long. I would not recommend doing it by hand. Easiest way to find the line of best fit is actually to do it on the calculator. You can also do this on Excel. I'm not going to go over that, but it is actually pretty simple to do using an Excel spreadsheet if you just put your data points into a spreadsheet. But we are actually going to do that on our calculators, and then the calculator can actually graph this for you. It can plot all of your data points, and it can actually draw that line of best fit through those points for you. It can give you the equation of that line of best fit. So this is the problem that we're going to be solving on our calculators. We're going to be finding a line of best fit for this particular data where we are comparing the number of stores for a particular pizzeria to their sales in millions of dollars. So we are going to assume here that the sales of a particular pizzeria are going to depend on the number of stores that they have, because we're going to assume that the more stores that they have, the larger the sales. So we're going to find a line of best fit for these data points where we're saying that the number of stores is going to be our X value, sales is going to be our Y value. And then we're going to use that line of best fit to estimate the sales if we think that this particular pizzeria has 4,000 stores, and then we're going to go the other way and estimate the number of stores that are needed in order for the sales to be $2 billion, which if we look, our sales are in millions of dollars. So that's going to be 2,000 million. Okay, so in order to do this and to find this line of best fit, first thing you need to do is to actually put the data points into the calculator. So the way that you do that is you're going to press this button Stat here and click Edit, so that first option on the menu. Pick whichever list you like. I'm sticking to list 1 and list 2. You may have to clear the lists. If so, go up to where it says L1 and click Clear and do the same with list 2. But what I have done is I've put all my X values, so the number of stores, into each of my entries in list 1, and then list 2 is made up of these Y values, so the sales in millions of dollars. Once you've done that, you have your X and Y coordinates in your lists. So you can go ahead and actually find that line of best fit. You're going to go back to Stat. I'm actually going to quit out of it. Go back to Stat, over to Calc, and go down to where it says Option 4, Linear Regression AX plus B. This is the form that we want our line of best fit in. So I'm going to click Enter. My X list, my list of X values, is a list 1. My Y list of Y values, is list 2. If you've put them into different lists, you will have to go ahead and change those. Just go into second list 1, second list 2, second list 3. You'll see that they're right above the 1, 2, 3, 4, 5, 6 buttons. You'll see L1 through L6. So you can just change whichever list you've put in there. So I've got my X list is list 1, my Y list is list 2. We don't want anything for our frequency list, so leave that blank. Here where it says store reg EQ, we would like to store our line of best fit equation so that we can go ahead and plot it later on. So what I want here is to form an equation. We're going to call it Y1, okay? You're going to go into where it says vars, go across to Y vars, function, and you can click any of these, and I'm just going to pick Y1. So it's going to store this particular line of best fit, the equation for it, as Y1. Go down and calculate, and here we have the values that we need. The values we need really are A and B. A is actually your slope M, and B is going to be your y-intercept. So I'm always going to round to 2 decimal places. So our slope of our line of best fit is 1.02, and our B value, that intercept, is going to be negative 923.48. So you can go ahead and write those down, and then we can come back and figure out the last couple pieces of our problem. What I first want to do before we do that is to plot it just so that you can see it. Okay, you should find, if you now come out of this and go into where it says y equals, you should see that your particular graph or function is actually stored in there. Okay, so keep that in mind. If I go to second stat plot, you want plot 1 to be on. You want this to be the type of graph that you are going to be doing, which in our case is a scatter plot. It is that first type. So make sure plot 1 is on. You've picked that particular type of graph, a scatter plot. Your X list is L1 and your Y list is L2. You can pick whatever mark you want. I'm then going to go ahead, come out of this, go back to my Y equals, and I'm going to hit graph. It will plot those points for you, and it will draw the line of best fit straight through it. Okay, so it just gives you a quick sketch of what this looks like on a graph. You can go ahead and do this by hand. It's not difficult to plot out the points, but the thing that would be difficult is finding that line of best fit. So it kind of shows you where it is in comparison to our points. Now we're going to go ahead and finish our problem, the last 2 parts of the problem, and then we are done. So like I said, I have rounded what the value of the slope and the y-intercept are to give us this as our line of best fit equation. Then it asked us, if there were 4,000 stores for a particular pizzeria, what would I expect the sales to be in millions of dollars? Well, I go ahead and I plug X is equal to 4,000 in for my number of stores, and I just figure out what Y would be for that particular X. Okay, again, this is an estimate because we have gotten this from our line of best fit. The next part of the problem said, if our sales were $2 billion, so that's 2,000 million, so Y would be 2,000, how many stores would I need, just as an estimate? This time I'm going to plug in Y is equal to 2,000, and I'm going to solve for X. As you're looking at a number of stores, I would definitely round this to a whole number. Always look at the context of the problem. And I get that X is equal to 2,866. So that is the number of stores I would need in order to make $2 billion in sales.